Hi, this is Professor Stugard, and today we're going to talk briefly about partial derivatives. Now, before we start talking about partial derivatives from Calc 3, let's go back and make sure we understand what we had learned way back in Calc 1 when we first started taking derivatives of problems. And if we can kind of go back and remember the processes that we used and how we kind of developed our skills for taking derivatives, that should help us now in Calc 3. So the first problem I want to look at is to take the first derivative of the function f of x equals 5x cubed. Now, if you're in Calc 3, you've probably already taken that derivative in your head, and it's just become automatic, which is awesome. That's the way it's supposed to be. And if we keep practicing, our partial derivatives in Calc 3 should also become pretty automatic for us. But I do want to, like I said, slow down a little bit and make sure that we understand what's actually going on and kind of review the notation that we use to properly express our derivatives. Now, when we say the first derivative, typically in Calc 1, we used our prime notation. So f prime of x equals, and then we also use that d dx notation as well. And that d dx notation means the derivative with respect to x. Some of our basic rules, again from Calc 1 when we're taking derivatives. First of all, we can always factor our constants outside of our differentiation problem. And we can also differentiate term by term for polynomials. So taking a look at, again, this notation from Calc 1, we pay special attention to what our variable actually is. Of course, our function is f of x. There's only one variable. Our variable is the variable x. And so we look for that everywhere. We see that f prime of x, we see the d dx, and then when we take that derivative, we're only really looking at, well, the x's. That's the only part that's going to affect my differentiation. That means that 5 is a constant. We know that we can factor that constant outside of our derivative. Then we're just taking the derivative of x to the third, which we should easily get to the result 3x squared. And then to just finish the problem, we simplify. And of course, 5, my constant that I factored out, gets multiplied back in. And my derivative is 15x squared. And like I said, that's probably completely automatic for you at this point. But it's worth noting how we actually got there and remembering what we had to do back when we were first learning derivatives, because we can apply those same ideas now to our partial derivatives. Now, with functions of 2 or more variables, and again, all these ideas we could absolutely extend to as many variables as we would like, although typically in Calc 3 we're just going to stick with just the two, x's and y's. Our partial derivatives are going to be calculated pretty much the same way they were in Calc 1, but we are going to have to use different notation. So let's look at an example. Let's say I'm given a function of two variables, f of x and y, which is equal to x to the fourth plus 5x y cubed. And we want to find that partial derivative with respect to x. The notation we're going to use now, we want to calculate f partial x of x and y equals partial x of my function x to the fourth plus 5xy cubed. Now, make a note of the two important differences. First, we can no longer use the prime notation. We can't use prime notation anymore because we have more than one variable. The prime notation only works when there's one variable and we automatically just know that it's the derivative. Now with our functions of multiple variables, we need to be very specific about denoting which variable we are taking the derivative with respect to. So on that left-hand side, we typically use subscripts instead of the prime notation. And on the right side, notice that we no longer use the letter D. We're now using this Greek symbol, which we're basically just going to say is the partial. So that right-hand side would say basically partial x of x to the fourth plus 5xy cubed. So how do I calculate this partial derivative with my new notation? Well, just like we did before, we want to pay special attention to our variable. And so anywhere we see that variable, again, we want to make special note because that's the part that's going to actually involve our derivative. So anywhere I see x, that becomes my variable. that means that anything else is now my constant. So my function, that 5 is a constant, and that y cubed is a constant now. Even though it's a letter, right? It's a y cubed. Because my derivative is with respect to x, that y cubed has to be treated as a constant. And now we just apply our rules from Calc 1. We're going to differentiate term by term and factor any constants that appear. So that means we're going to take the derivative with respect to x of x to the fourth. And then with the other term, we factor out the 5 and we factor out the y cubed and take the derivative with respect to x of x. Now, the derivative of x to the fourth we know is 4x cubed. The derivative of x with respect to x is just 1. And so my answer is that the partial derivative with respect to x of my original function is going to be 4x cubed plus 5y to the third. All right, so let's take a look at that same function again, but now let's take the partial derivative with respect to y. Again, take note of the notation. First of all, we have to use that subscript again, and now it's with respect to y, so my subscript is y. And that partial notation on the right-hand side is again switched to partial y. We want to pay special attention to what our variable is. And again, if we keep practicing, this should become automatic. But our variable is clearly y, which means everything else is our constant. X to the fourth is our constant, and 5x is our constant. We're going to do the same thing we did before, split and factor our constants. And again, this step is going to become automatic if you've practiced enough, so you're probably going to end up skipping it. But for now, let's make sure we know exactly what's going on. So I can factor the x to the fourth from my first term, which just leaves me with, well, 1, because my term was just x to the fourth. And from the other term, we can factor the 5 and the x, because those are now my constants. Now we take the derivative with respect to y. But for that first term, the derivative of a constant is always going to be 0. And again, hopefully we can do this in our head, but the derivative of y cubed is 3y squared. And so when we simplify, again, we can multiply through with that 5x. We're not going to write 0 again. And so my partial derivative with respect to y is going to be 15x y squared. Now the notation. To simplify the notation, oftentimes instead of writing that this is a function of x and y, and we're taking the partial with respect to x, we're just going to write the subscript notation, just to make it a little bit neater. Now, given that my function of two variables is typically given as z equals f of xy, there are a lot of other forms of this notation that we use as well. So there's the, again, just partial x, there's the partial x of f, partial x, or even partial z partial x. There are even further notations as well involving a capital D, but we are not going to use that all that often, so we're not going to worry about that today. Now let's talk about higher partial derivatives. So just like in Calc 1, I could find the first derivative and the second derivative and the third derivative of a function, we can take higher partial derivatives in much the same way. Now, when we find our second partial derivative, again, we have to make sure that we clearly define what our variable is that we're taking the derivative with respect to. So what this means, for example, is that we can find the first partial derivative with respect to x, but then find the second partial derivative with respect to y. Our notation that we're going to use would be then f partial x partial y, which usually is just simplified as f partial xy. And again, that means we're taking the derivative with respect to x first, then with respect to y second. And so again, we're pretty much going to read that partial notation from left to right. And it's going to tell us the order in which we should be taking our partial derivatives. So let's take a look at that same function from before and find some second partial derivatives. So let's find that partial derivative f partial xy. Now the first thing we need to do is find the partial with respect to x. We did that already, so I'm just going to take our result from earlier. And now the second step is going to be to take that partial derivative of f partial x, but now do it with respect to y. So that really means, again, notational wise, we're doing f partial xy, which is really the partial derivative with respect to y of f partial x. So we're just going to substitute in the function that we had found earlier as our partial derivative with respect to x, and now take that derivative with respect to y. Again, basically following all of our steps that we learned from before. So my first term is the 4x cubed. There is not a single y in there, which means 4x cubed is a constant, which means the derivative of that constant is just going to be 0. And then the derivative of 5y cubed, 15y squared, and so simplifying, we wouldn't write the 0. We would just write that our partial xy is equal to 15y squared. Now let's swap it. Now I want to find the partial derivative f partial yx. Now again, we're reading this from left to right for my partials, which means the first thing I need to do is find f partial y. Again, we found that just a minute ago, so we're just going to basically use that again. And now the second step is going to be to find the partial of that result, now with respect to x. Notationally, this is what it should look like. Again, we're taking the partial with respect to x of that partial with respect to y, plug in our function, and again, we're looking at this derivative with respect to x, so that means anything that's not an x is a constant that can be factored, which means I'm factoring the 15 and the y squared, and then I'm just taking the derivative with respect to x of x. But the derivative with respect to x of x is just going to be 1, which really isn't going to change anything. So my second partial derivative here is going to be 15y squared. So again, given that same function, we found that partial xy was 15y squared, and partial yx was 15y squared, which means, well, those two second partials were actually equal to each other. Is that a coincidence? No, not at all. This is actually a very, very important result called Clairaut's theorem. Clairaut's theorem, in about as basically as I can write it, if we have a continuous function of two variables, and if the second partials, xy and yx, are both continuous, then they must be equal to each other. Now, the function does not necessarily have to be continuous everywhere, but on the intervals for which it is continuous, this theorem will hold true for all points. So for partial derivatives, the main ideas you want to take away. First, we're going to use all of our previous rules for finding derivatives, meaning the power rule, the product rule, the quotient rule, the chain rule, the trig derivatives, the exponential derivatives, the logarithmic derivatives. We're going to use all of those rules again. And we need to be masters at applying those rules. That doesn't mean that we have to be able to take first derivatives and get the answer correct. What that means to be a master and to do well, to have mastered the skill, is to be able to take those derivatives and never get a wrong answer. So there's a little bit of a difference. I'm not saying that you need to get the right answer. I'm saying you need to never be wrong. And however much practice that takes you to become an expert, that's the amount of time you need to spend practicing these derivatives. The second thing that we want to make sure that we're very, very careful about is clearly defining the variable and using the proper notation. We've got to make sure that we use the proper notation here. We've got to be neat, we've got to be organized, and because we're using subscripts and multiple subscripts, and we'll have exponents, write big, write clearly, and make sure you're using the proper notation. Proper notation counts. And the main idea, again, taking these partial derivatives, if we know all of our rules of derivatives, we should be in really, really good shape, because anything that's not that variable that we're looking at gets treated like a constant. And we know that the derivative of any constant is 0. And we also know that we can factor constants out of any expression. So we're going to use those two rules, well, quite frequently. And then the last thing to remember is Clairaut's theorem. Clairaut's theorem is really, really important anytime we have to take second derivatives, which, spoiler alert, is going to come up when we talk about optimization problems or finding mins and maxes. And if you remember back from Calc 2, that second derivative rule, well, yeah, there's going to be a second derivative rule here for our partial derivatives as well in our functions of two variables. And Clairaut's theorem can make our lives way easier if we recognize which order would make our lives better. And even more importantly than that, when we get to taking multiple integrals, there is a similar theorem called Fubini's theorem that basically applies the same idea, that we can take our integrals in either order as well, which is almost more important than Clairaut's theorem, but worth practicing. So give these partial derivatives a shot. Again, practice, practice, practice. You should be taking hundreds of derivatives till you become that expert, and good luck.